Hello everyone. In the journey of understanding the concepts of class 9th maths curriculum, we have already completed first 9 chapters of the syllabus. So today we are here with the 10th chapter, that is circles. So let's start it. So before starting, one should know what circle is. In our day-to-day life, we come across so many round things. Like coins are there, like bangles are there, like clocks are there. So many round things are there. So what all are the parts of a circle? What all it is composed of? What all are the properties of a circle? That all we will be understanding in this video. So what circle is? Basically, if we will be taking a plane, and in this plane, collection of all the points which are at a fixed distance from a fixed point is known as your circle. That means suppose I have taken a fixed point, this is the fixed point. And if I am saying that from this fixed point, what all are the points which are at 2 centimeter from this fixed point. So suppose I am taking all the points, these will be the points which are at 2 centimeter from this fixed point. If I'll be joining all these points, the figure which I will be getting is a circle. That means we have taken a fixed point, and from this fixed point, what all are the points which are at equal distance. If we will be joining all these points, the figure which we will be getting will be a circle. This fixed point is known as center of the circle. This is center of the circle, and this fixed distance from here, from center to this boundary, this is known as your radius of the circle. This is radius of the circle. That means the fixed point which we are talking about is your center of the circle. This is the fixed point, and the fixed distance which we are talking about is the radius of the circle. If we will be joining the center of the circle with any point on the boundary of this circle, it is your radius. The line segment joining the center of the circle to any point on the circle, if we will be joining these 2 points, it will give us radius of the circle. So from here, if I'll be joining this point, then this will even be the radius of the circle, and all the radius of the circle will be of the equal measurement because it is a fixed distance. So that's the reason all the radius of a circle will be of the fixed measurement. So this is your circle is. If we'll be taking a circle in any of the plane, then this is dividing the plane into 3 parts. Suppose this is a plane. This is a plane we have taken, and in this plane we have taken a circle. Then this circle is dividing this plane into 3 parts. One will be the interior of the circle. This is your interior of the circle. That is your, another is your on the boundary we are talking about, you're on the circle. It is on the circle. And another is your exterior of the circle. That means if we will be drawing any circle in a plane, then it is dividing the plane into 3 parts. One is which is inside the circle, will be the interior of the circle, which is coming on the circle, on the boundary. We are saying it to be on the circle, and the another one which is outside the circle will be known as your exterior of the circle. Just now we said that if from the center we will be joining any of the point on the circle, on the boundary of the circle, then it is your radius. So if the distance of any of the point in the plane, if we are talking about any of the point in the plane, suppose one point I am taking here, one point I am taking here, one point I am taking here, then here, then here. So if the distance of the point in any of the plane from the center of the circle is less than the radius, then it will be, the point will be in the interior of the circle. So from here, this is your radius from here to here. Suppose this is your point O, and this is your radius of the circle. So if this is your point P, then OP, this OP, distance of the point from the center of the circle, because it will be less than your radius. So OP is less than your radius. That's the reason this point P will be in the interior of the circle. Similarly, if I'll be taking a point, suppose this is the point Q, and distance of this point from the center, this is your OQ, because OQ will be equivalent to your radius. So we will say that this point Q is on the circle, or we will say it is on the boundary of the circle. It is on the circle because distance of the point from the center of the circle is equivalent to the radius. Now, if we are going to take this as the point, and this is suppose your point R, and the distance of this point from the center of the circle, because it is your OR, because it is your greater than radius, so we will say OR is greater than your radius. That's the reason this point R will be in the exterior of the circle. So a circle is dividing a plane into three parts. Which is inside the circle will be the interior of the circle, on the circle, and your exterior of the circle. The part which is outside the circle will be your exterior of the circle. Now, if the distance of the point from the center of the circle is less than your radius, then the point will be in the interior of the circle. If the distance of the point from the center is equivalent to the radius, then we will say that the point is on the circle. And if the distance of the point from the center is greater than your radius, then we will say that it is in the exterior of the circle. This whole boundary of the circle is known as your circumference. It is known as circumference. As we say the perimeter of any of the closed figure, plane figure, similarly we'll be talking about the perimeter of this circle. That means if you start from here, move on the boundary of the circle and come back here, the distance covered by us will be known as your circumference of the circle, and it is given by your 2 pi r, where r is the radius of the circle and pi is a constant whose value is your 22/7. So this is about your circle. That means if a circle is we are making in a plane, then how much parts it is dividing it into. So this is all about. We know about the radius, about the center of the circle. Now let's see some of the parts of it. What is chord? Now suppose we have taken this as a circle. This is the center of the circle. If we have taken on the boundary of the circle, we have taken any 2 points. Suppose these are the 2 points. This is your point P and this is your point Q. And if we will be joining these 2 points, the line segment PQ will be known as chord of the circle. That means on the boundary, boundary of the circle, if we have taken any 2 points and we have joined them, then the line segment joining these 2 points will be known as your chord of the circle. Now, if we will be moving towards the center of the circle, the length of this chord will keep on increasing. That means this PQ, and suppose this is your ST. So ST will be greater than your PQ. And if we will be going away from the center, that means suppose I am talking about these 2 points, that is your AB. If I will be taking AB as the chord, then length of AB will be smaller than your PQ and PQ will be smaller than your ST. So the chord which will pass through the center of the circle, if we will be talking about a chord which will pass through the center of the circle, suppose this is your CD, is known as diameter of the circle. That simply means if we will be taking the chord which will pass through the center of the circle, it is known as your diameter of the chord. And diameter of the chord is the longest chord. Diameter of the circle. Diameter of the circle CD is even a chord because we have taken 2 points on the boundary of the circle, that is C and D, and we have joined this and it is passing through the center, so it is even one of the chord, and this will be the longest chord of the circle. That means diameter is the longest chord of the circle. Longest chord of the circle. Now again, if we will be moving away from the center, that means if we will move from here to here, from here to here, then again the length of the chord will keep on decreasing. From here to here, if we are moving from here to here, it is increasing. Then CD, which is the diameter of the circle, will be the longest chord. Then again the length of the chord will keep on decreasing. So simply we can come to know if we will be taking any 2 points on the circle and if we are going to join them, the line segment will be the chord and the longest chord will be the diameter which will pass through the center of the circle. Now if we are going to see over here from O to C, this is radius of the circle, because from the center, if we will be joining the center with any of the point on the circle, then it gives us the radius. So OC is the radius of the circle. Similarly, OD will even be the radius of the circle. That means diameter is equivalent to your 2 times of your radius. If we will multiply radius by 2, we will be getting the length of the diameter. Diameter is always your twice of the radius. And in a circle, we can draw infinite of diameters. CD is one of the diameter. If we will be taking this line, this chord, then it is even a diameter. If we will be taking this chord, then this is even a diameter. Also, all the line segment which will touch the circumference at 2 points and pass through center will be the diameter. So in a circle, infinites of diameter we can draw, and length of all the diameters will be equal. Every diameter will be of the equal measurement. This is about your chord and diameter. Now arc. Now if I'll be taking a circle, suppose this is a circle, and I'm taking any 2 points over here on the boundary of the circle. Suppose this is the center of the circle O. Then the part of the circle, or the piece of the circle, or the piece of the circumference, a part of the circumference which it is joining, like P and Q I am taking. These are the 2 points on the boundary of the circle. Then this part of the circle is known as arc. This PQ will be the arc. It is dividing the whole circumference or whole boundary of the circle into 2 parts. One will be your this one, which is a smaller one, and another is your PQ, which is this bigger one. So this smaller one is known as your minor arc. This smaller one is known as your minor arc. And it will be denoted by, because PQ is there, so it will be denoted by PQ, and this is the denotation for your arc. This is your minor arc. And now this is PQ. This PQ will be the bigger part, so it is your major arc. So how to denote the major arc? Because even for the major arc, the starting and the ending point are P and Q only. So for denoting any of the major arc, we take another point also, anywhere on the major arc. Suppose it is your arc and it is lying over here. So we will be saying the major arc will be your PRQ. This will be the major arc. So whenever we are simply writing arc PQ, then simply we are talking about your minor arc only. We generally, if we are denoting the major arc, we will specify that it will be a major arc. So if we have taken any 2 points on the boundary of the circle, then the part of the circle, the part of the circumference is your arc. If it is a smaller one, so it will be the minor arc, and if it is a bigger one, it will be your major arc. And if these 2 points are the end points of a diameter, suppose if I'll be joining these 2 points, then it will be passing through your center of the circle. It will be the diameter. And suppose I'm saying that this is your A and this is your B. Then this arc AB, because it is dividing this whole boundary into 2 equal halves. It is going to divide it into 2 equal halves, because diameter, if I'll be making diameter like this AB, then it will be dividing the whole circumference, whole boundary of the circle into 2 equal halves. So this arc will be known as your semicircular arc, or it will be your semicircle. AB, whether I am going to take from here to here or I am going to take from here to here, both the lengths will be equal. So it is known as your semicircle, because it is dividing it into 2 equal halves. So if the 2 points which I have taken on the boundary of the circle are the endpoints of the diameter, then this arc will be dividing it into 2 equal halves, and that's the reason this arc will be known as your semicircle. If I'll be talking about this, it is even a semicircle, and if I'm talking about this, then also it will be a semicircle. So this is all about your arc. Now comes your segment. Now suppose this is a circle, this is the center of the circle, and I have taken 2 points on the circumference of the circle, or I have taken a chord. I have taken these 2 points and I have joined these two. So PQ will be the chord of the circle, just now we have discussed. So region of the circle which is enclosed between the arc and the chord is known as your segment. The region which is enclosed between your chord and the arc, is known as segment. If we are taking the minor arc, PQ, this PQ is the minor arc, then this area which is corresponds to your minor arc will be known as your minor segment. And if I am the region we are taking is corresponding to your major arc, that means if we are taking corresponding to this, that means we are talking about this region, then it will be your major segment. It will be your major segment. So the region between the chord and the minor arc will be the minor segment, and the region between the chord and the major arc will be your major segment. So this is how again a chord is dividing into two segments also. If it is corresponding to your minor arc, then it will be your minor segment. As we can see, this is smaller, we can just compare it even. And if we are corresponding to the major arc, because this is your major arc and this is the chord, so region between the major arc and the chord will be your major segment. Now again, if this chord is your diameter, that means instead of this PQ, if we will be considering this diameter, this is O, center of the circle, and this is your, suppose AB is the diameter of the circle, then again it is dividing it into two equal regions. That means the region over here above the diameter and below the diameter, they will be equal. That's the reason they are known as your semicircular region. Semicircular region, because it is dividing into two equal halves, two regions of equal measurement. That's the reason if the chord is your diameter of the circle, in that case these two regions will be equal and it will be known as your semicircular region. Now coming to your sector, if this is a circle, this is the center of the circle, then the region enclosed between two radius and the arc. Suppose this is your point P and this is your point Q on the boundary of the circle. So PQ will be the arc and these OP and OQ are the radius of the circle. So the region enclosed between the arc and two radius of the circle, which is joining center to the end points of the arc. P and Q are the endpoints of this arc. For this minor arc, P and Q are the endpoints. So the radius joining the center to the endpoints of the arc and the arc, the region enclosed between this is known as your sector. This is sector. Now again, if this sector is corresponding to your minor arc, then it will be your minor sector. If the sector is corresponds to your minor arc PQ, then it will be your minor sector. And if we are taking the region enclosed between the major arc and the two radius, then it is your major sector. If it corresponds to minor arc, it will be the minor sector, and if it corresponds to the major arc, then it will be your major sector. As just now we can see, this is smaller one, this will be the bigger one, so that's the reason it is your major sector and this is your minor sector. Now again, if your OP and OQ, these are forming the diameter of the circle. That means if the two radius we are talking about, if this is the two radius, this is the center of the circle, and suppose your A and B are the diameter. AB is the diameter which is passing through the center of the circle, that is O. So we will be saying OA is the radius and OB is also the radius. So the region enclosed between these two radius OA, OB and the corresponding arc, that is this will be the corresponding arc, it will be equal. It will be dividing the whole circle into two equal halves. This above region will be equivalent to your below region. OA and OB are the radius of the circle, but AB is the diameter of the circle, and diameter divides the circle into two halves. So this region between AB and this your circular region, that is your arc AB, this will be your semicircular region. It will be known as semicircular region, because again it is dividing into two halves. This AB is your semicircle. Just now we had learned that if your arc is dividing it into circumference into two equal halves, then we say it to be a semicircle. So if we are taking a semicircle, AB semicircle we are talking about, and this AB diameter we have taken, that means two radius are your OA and OB, which together is forming the diameter of the circle, then it will be dividing the whole circle into two equal regions, and they will be known as your semicircular region. So hope it is clear to you what circle is, what is center of the circle, what is radius of the circle, what is chord, what is arc, segment and sector. So now we'll be learning in this chapter so many properties, so many theorems related to circle and the chord. So let's see how we can prove all these properties. Now let's understand some of the questions from your exercise 10.1. Question number 1, that is fill in the blanks. The center of a circle lies in dash of the circle. So obviously we know that the center of the circle lies in the interior of the circle. We have already discussed that if this is a plane, and if in a plane we have taken a circle, we have drawn a circle, then this circle is dividing the plane into three parts. The part which is inside the circle is known as interior of the circle. The part which is on the circle or boundary of the circle, which is known as your circle, and the part which is outside the circle is known as your exterior of the circle. Together your interior of the circle and the boundary is known as your circular region. If we will be taking together the part which is inside the circle and which is on the circle, that means boundary of the circle, this together is known as your circular region. And center lies over here, that means it is in the interior of the circle. A point whose distance from the center of a circle is greater than its radius lies in the exterior of the circle. We had discussed that this distance from here to here, any point on the boundary of the circle, if we will be joining with the center, it gives us the radius. And if the point we have taken, suppose over here, so distance of this point from the center is your greater than your radius, that's the reason this point will be in the exterior of the circle. If the distance of the point from the center is greater than radius, then the point will be in the exterior of the circle. The longest chord of a circle is a diameter, we had discussed. An arc is a dash when its ends are the endpoints of a diameter. So the arc will be your semicircle when its ends are the ends of a diameter. If we will be taking this, these are the ends of the diameter. Suppose these are the ends of the diameter, then the part of the arc, it is dividing the whole circumference into two equal halves. So it will be known as your semicircle. This is done. Then segment of a circle is the region between an arc and the chord of the circle. We had discussed that if we will be taking any of the chord, then the region enclosed between the chord and the arc of the circle is known as segment. A circle divides a plane on which it lies in three parts. One is interior, another is on the circle, and third is exterior. Together the interior of the circle and the boundary is known as your circular region. Now let's see the angle subtended by a chord at a point. What it is, how we say what angle is known as your angle subtended by a chord at a point. Now suppose I have taken any 2 points and I have joined it. So it will be the line segment AB. If its name is your AB, then AB will be the line segment. If I'll be taking any another point C, which is not on this line segment AB, suppose this is the point C, and if I'll be joining this AC and this CB, then the angle ACB will be the angle subtended by the line segment AB. Then this angle ACB will be known as angle subtended by the line segment AB on the point C. Now similarly, if I'll be taking this circle, and in this circle, suppose this is O is the center of the circle, and this is your AB, which is chord of the circle. Then it is your AB, this AB will be the major arc and this AB will be your minor arc. It is a smaller one. So this part of the circle is your minor arc and this part of the circle is your major arc. Now the angle, suppose I am going to take any of the point on the minor arc. Suppose this is your point, say C, and on the major arc, suppose I am taking this point as D. Then if I'll be joining the endpoints of this chord AB with this C like this, if I'll be joining it, then this angle ACB will be angle subtended by the chord AB on the minor arc at the point C, because it is your minor arc. So at the point C, this chord AB is making an angle of your ACB. So it will known as your angle subtended by the chord AB at the point C. Similarly, on the major arc, I have taken a point D. So if I'll be joining the endpoints of this chord AB with D, like this, I have joined it. Then this angle ADB, this angle ADB is the angle subtended by the chord AB at point D. This is how we just represent it. If AB is the chord, we have taken a point in the minor arc, point C, and if I'll be joining AC and BC, then angle ACB will be the angle subtended by the chord AB at point C. Similarly, if I have taken a point D anywhere else on the circumference of the circle, and if I'll be joining AD and DB, that means endpoints of the chord I'll be joining with this point, then angle formed, that is your ADB, will be the angle subtended by the chord AB at point D. Now, if this O is the center of the circle, if I'll be joining this center of the circle with the endpoints of the chord, then the angle formed will be your angle AOB. So this angle AOB is known as angle subtended by the chord AB at the center. This angle AOB is angle subtended by the chord AB at the center. So hope it is clear. If we have taken a chord AB in a circle, and if we are joining the endpoints of these two chords, these and 2 points of the chord, if we will be joining with any other point on the circumference of the circle, suppose we have taken a point D over here and we have joined AD and BD, then this angle ADB will be the angle subtended by the chord AB at point D. And if I have joined this AC and BC, then the angle formed ACB will be the angle subtended by the chord AB at point C. Similarly, if we have joined the endpoints of the chord AB with the center, then the angle formed AOB will be known as angle subtended by the chord AB at the center. This is how we can represent it. Now we will be seeing some properties related to it. Now let's understand some of the theorems related to it. Theorem 10.1. Equal chords of a circle subtend equal angles at the center. That means if there are two chords of a circle which are equal, then at the center they will be subtending equal angles. That means if in a circle AB and PQ are the two equal chords, then the angle subtended by the chord AB at the center, that is angle AOB if it is angle 1, and angle subtended by the chord PQ at the center, that is angle POQ, that is angle 2, are equal, that we need to prove. So over here it is given to us that chords AB is equivalent to PQ. It is already given to us, and we have to prove that angle AOB is equivalent to angle POQ. This we need to prove. So what we will be doing is we will be taking these two triangles. One of the triangle we will be taking as AOB. Another triangle we will be taking as POQ. In these two triangles, it is already given that AB is equivalent to PQ. They are equal. It is given to us that the chords are of equal measurement. Equal chords. It is given to us. Now, if we will be seeing these two triangles, then OA is the radius of the circle and OP is even the radius of the circle, because it is starting from the center O and touching the points on the circumference of the circle. So OA, OB, OP, OQ all are radius of the same circle, and we know that if we are talking about a same circle, so means one circle, then all the radius will be of the equal measurement. So in these two triangles, triangle AOB and triangle POQ, OA will be equivalent to OP because they are radius of the same circle. Similarly, in these two triangles, OB will be equivalent to OQ because again, they are radius of the same circle. So we can see all the three sides of this triangle is equivalent to all the three corresponding sides of another triangle. So that's the reason we can say that triangle AOB will be congruent to triangle POQ by SSS congruency rule. And we know that if two triangles are congruent, then their corresponding parts are even equal. So we can say by CPCT, that is corresponding parts of congruent triangles. CPCT means corresponding parts of congruent triangles. We can say that angle AOB will be equivalent to angle POQ, and that was to be proved. Because see, corresponding angles will be angle 1 is corresponding to angle 2 in these two triangles. So we can say that these two angles will be equal as the triangles are congruent. So this is how we can prove it. Now let's see the converse of it, the theorem 10.2. If the angles subtended by the chords of a circle at the center are equal, then the chords are even equal. Over here it is given that AB and PQ are any two chords of a circle, and angle subtended by the chord AB at the center is your AOB, that is angle 1, and angle subtended by the chord PQ at the center is your POQ, that is your angle 2. These two angles are equal. It is already given to us that angle 1 is equivalent to angle 2. We have to prove that the chords will be equal. That means if there are two chords in a circle and angle subtended by these two chords at the center is equal, then the chords will even be equal. Now given to us is that angle AOB is equivalent to angle POQ. That means angle 1 is equivalent to angle 2. It is given to us. We have to prove that AB is equivalent to PQ. This we need to prove. So what we will be doing, again we will be considering these two triangles. We will be taking triangle AOB and triangle POQ. In these two triangles we can see OA is equivalent to OP because they are radius of the same circle. Similarly, OB of triangle AOB is equivalent to OQ of triangle POQ because they are even the radius of the same circle. Now, in these two triangles, OA is equals to OP, OB is equivalent to OQ, and it is already given to us that angle AOB is equivalent to angle POQ. So, we can see that SAS, by SAS congruency rule, the triangle AOB will be congruent to triangle POQ. Here the angle is your included angle. So side angle side congruency rule, we can say that these two triangles will be congruent. And we know that if triangles are congruent, we can see that by CPCT, the corresponding parts will even be equal. CPCT, corresponding parts of congruent triangles, will even be equal if triangles are congruent. So we can say that AB will be equivalent to your PQ because AB corresponds to your PQ. So this is how we can prove that if the angles subtended by any two chords of a circle at the center are equal, then the chords will even be equal. Now let's see one of the questions from your exercise 10.2. Recall that two circles are congruent if they have the same radius. We have just now learned that in your chapter number triangles, in chapter triangles, we have learned that what all are the rule for your congruency, and if there are two circles which are having the same radius, then the circles will be congruent. That already we have learned in the chapter. Now prove that equal chords of congruent circles subtend equal angles at the center. So what we need to prove is, instead of one circle, there are two circles whose radius are equal. And if radius are equal, then they will be congruent. That means we are talking about two congruent circles we are talking about. So we have taken two congruent circles. This is not properly made. So we have taken two congruent circles we have taken. Now in these two congruent circles, there are two chords which are of equal measurement. Suppose this is one of the chord in this circle and this is the chord in this circle, and the measurement of these two chords are equal. That means if this is your AB and this is your CD, then it is given to us that AB is equivalent to CD, and for both of them radius is even equal because they two are your congruent circle. So radius are even equal for both the two circles. subtend equal angle at the center. That means the angle they are forming at the center will be equal. Now, if AB is the chord of this circle with the center O and CD is the chord of a circle with center P, in which AB is equivalent to CD and radius for both the two circles is even equal because your circles are congruent. So the angle they are forming at the center, angle subtended by the chords at the center will even be equal, that we need to prove. So we have to prove that angle 1 is equivalent to angle 2. And if this OA is R, so OPC is even R. It is given to us. And AB is equivalent to CD. It is even given to us. So given to us is AB is equivalent to CD. It is given to us. Both are having the same radius. So OA is equivalent to your PC. It is even given to us because they are having the same radius. Now we have to prove that your angle 1 is equivalent to angle 2. That means angle AOB will be equivalent to angle CPD. Now we are considering these two triangles. One of the triangle we are considering triangle AOB and triangle CPD. These two triangles we are considering. In these two triangles, AB is equivalent to CD. It is given to us that the chords are of equal measurement. The two circles are congruent and they are having the congruent same length of your chords even. That means AB is equivalent to CD. It is given to us that the chords are of equal measurement. Now OA of this triangle AOB, it is equivalent to PC of the triangle CPD because they are radius of congruent circles. They are radius of congruent circles. Now in the triangle AOB, OB will be equivalent to, in the triangle CPD, it is equivalent to your PD. Again, because they are radius of the congruent circles. Now we can see in these two triangles, all the three sides are equal. The corresponding sides of one triangle is equivalent to the corresponding sides of another triangle. So we can say that triangle AOB will be congruent to triangle your CPD by your SSS congruency rule. Both the triangles will be your congruent. And if both the triangles are congruent, we can say that by CPCT, their corresponding parts will even be equal, or we can say angle AOB will be equivalent to angle your CPD. So if instead of one circle, here we had taken that if in a one circle only there were two chords which were of equal length and they were making an equal angles at the center. Now instead of this case, we have taken two circles which were congruent, and in these two circles we have taken one chord and the length of the chord was even equal. So instead of one circle, we could have taken two circles also, and the two circles are congruent also. It is given to us in the question, and the two chords which they are making are even equal. So we can prove this way, means almost it is a similar way. We can prove that the angle subtended by these two chords at the center will even be equal. Now let's see some other properties of circle. Theorem 10.3. The perpendicular from the center of a circle to a chord bisects the chord. So over here we are having a circle with center O in which AB is the chord. If from the center of the circle we have drawn a perpendicular, that means which is making an angle of 90 degree on the chord, then we have to prove that it is going to, OC is going to bisect your chord AB. That means AC will be equivalent to your CB. That means if from the center of the circle we are going to draw a perpendicular on the chord AB, then it will be bisecting the chord. So what is given to us is we are having a circle whose center is your O and AB is the chord of the circle. And it is even given that OC is perpendicular to your AB. That means these angles are your 90 degree. Perpendicular means 90 degree angle they are making. So this angle OCA will be equivalent to your OCB. They are your 90 degrees. It is given to us. We have to prove that AC is equivalent to CB. This we need to prove. So what we will be doing is we will be taking these two triangles. One of the triangle we are taking as AOC, another triangle we are taking as BOC. These two triangles we have taken. In these two triangles, OA will be equivalent to OB because they are radius of the same circle. OA is even the radius and OB is even the radius of the same circle. OC is common for both the two triangles. For the triangle AOC also, and for the triangle BOC also, OC is common. And here it is already given that OC is the perpendicular. So angle OCA will be equivalent to OCB, that will be your 90 degree. So we can say that by RHS congruency, these two triangles will be congruent because side opposite to this 90 degree, that is your hypotenuse OA is equivalent to hypotenuse OB. Hypotenuse are equal for both the two triangles. Angle is 90 degree and one of the side, that is OC, is common for both the two triangles. So your RHS congruency we can apply over here. So we can say that by RHS congruency, the triangle AOC will be congruent to triangle BOC. These two triangles will be congruent. And we know that if the triangles are congruent, then their corresponding parts are even equal. So we can say that by CPCT, your AC will be equivalent to your BC. That means C is the midpoint of your AB, and that was only to be proved that this perpendicular is bisecting the chord. That means OC is dividing the chord AB into two equal halves. So we have proved AC is equivalent to BC. This is how we can prove it. Now the next theorem, theorem 10.4, just converse of it is, the line drawn through the center of a circle to bisect a chord is perpendicular to the chord. Over here it is given that from the center we are going to draw a line. Simple, a line is given on the chord AB, which is bisecting the chord. That means C is the midpoint of AB. It is given to us that AC is equivalent to CB. It is given that from the center we have drawn a line on the chord AB, which is bisecting the chord. That means C is the midpoint of your AB. We have to prove that this OC is perpendicular to your OAB. Now given to us is that there is a circle whose center is O and AB is the chord and your C is the midpoint of AB. That means AC is equivalent to BC. It is given to us. We need to prove that OC is perpendicular to your chord AB. How we can prove it? Again, we will be considering these two triangles. One of the triangle AOC, another triangle BOC. In these two triangles, OA of triangle AOC is equivalent to OB of triangle BOC because they are radius of the same circle. So OA will be equivalent to OB. OC is common for both the two triangles, for the triangle OAC also and for the triangle BOC also. OC is common for both the two triangles. And AC is equivalent to CB. It is already given to us that C is the midpoint of AB. It is bisecting the chord AB. That means AC is equivalent to BC. It is already given to us. So we can see in these two triangles, three sides of this triangle are equal to the three sides of this corresponding sides of this triangle. So we can say that by SSS congruency, the triangle AOC will be congruent to triangle BOC. These two triangles will be congruent by SSS, side congruency rule. They will be congruent. And we know that if the triangles are congruent, then their corresponding parts are even equal. So we can say that by CPCT, suppose this is your angle 1 and this is your angle 2. So angle 1 will be equivalent to your angle 2. Angle ACO, that is your angle 1, is equivalent to angle BCO, that is your angle 2. We can say angle 1 will be equivalent to your angle 2. Now we are going to see over here, these angle 1 and angle 2 are your linear pair of angles. That means sum of angle 1 and angle 2 will be your 180 degree. So angle 1 plus angle 2 will be your 180 degree because they are your linear pair of angles. And just now we have said that angle 1 is equivalent to angle 2. So instead of angle 2 also I can write angle 1 only. So it will be angle 1 plus angle 1 is 180. Or we can say 2 times of angle 1 is 180 degree. Or we can say angle 1 is 180 divided by 2, that is your 90 degree. And if angle 1 is 90 degree, angle 2 is equivalent to angle 1. So both the angles 1 and 2 are your 90 degree. And if this angle is 90 degree, that means OC is perpendicular to your AB because it is making an angle of 90 degree. So we can say that OC is perpendicular to OB. Over here I have written angle 1 as your angle ACO and angle 2 as your angle BCO. So same thing it is. Instead of ACO I could have written angle 1 also, and instead of BCO angle I could have written angle 2 also. So sum of these two angles will be 180 degree because they are linear pair of angles, and just now we have said, we have proved that these two angles are equal by CPCT. So instead of the another angle we can replace this by your ACO only, and 2 times of ACO will be 180 degree, or we can say angle ACO is your 180 by 2, that is 90 degree. And if these angles are 90 degree, we will be saying that OC is perpendicular to your OAB, and that was only to be proved. So this is how we can prove it. Now let's see how many circles can be drawn through the given points. We have already learned that if there are 2 points are given to us, then passing through these 2 points we can draw a unique line. That means a unique line can be drawn through any 2 given points. Now if any 1 point is given to us, let's see how many circles can be drawn if any 1 point is given to us. Suppose this is a point O, and we can see that this point O, we can draw infinite of circles can be drawn through a given points. So similarly we can see if there are any 2 points given to us, then passing through these 2 points we can draw so many circles can be drawn through these 2 given points. Now if 3 points are given to us, and if these 3 points are collinear, that means if we can draw a line passing through all these 3 points. Now let's see how many circles can be drawn passing through these 3 points. So if we will be seeing, then passing through all these 3 points we cannot draw even a single circle. If we will be taking these 2 points, then we can draw a circle passing through these 2 points. In that case, this point will be outside the circle. If this is your A, this is your B, and this is your C. If we will be considering these 2 points, then passing through these 2 points even we can draw a circle. But in that case, your point A will be outside the circle. And if we will be considering A and C as the points, then again we can draw a circle passing through these 2 points. But in that case, point B will be the inside the circle. So passing through these 3 points, we cannot draw a circle if the given 3 points are your collinear. But if the 3 points given to us are not collinear, then let's see how we can draw a circle. Suppose these are the 3 points which are non-collinear points. Suppose this is your A, this is your B, and this is your C points. Then what we can do is we can join these points. Suppose I have joined AB and I have joined BC also. These two I have joined. I have joined AB also and I have joined BC also. Now what I will be doing is I will be drawing the perpendicular bisector of AB. So we know how to draw the perpendicular bisector of any of the given line. We will be taking this as the center and more than half of the AB as the radius. Then I will be making an arc here from A. With the same radius but with the center B, I will be making an arc which will be intersecting the previous arcs. Suppose these are intersecting at these points, and this is the line which we are getting when I will be joining these 2 intersection points. So this line, suppose this is your P and Q. So this PQ is the perpendicular bisector of AB, and we know the property of perpendicular bisector that every point on this line PQ will be equidistant from the point A also and from the point B also. Suppose I am considering this as the point D, then distance of AD will be equivalent to your BD, because whatsoever the point will lie on this line PQ will be equidistant from A also and will be equidistant from B also. Similarly, now what I will be doing is I will be making the perpendicular bisector of BC. Now taking B as the center and more than half of the BC I will be taking as the radius. One of the arc here, one of the arc here. From the C also with the same radius, I will be making an arc here and one arc here. Suppose they are intersecting at these points, I will be joining these 2 points, and this is the perpendicular bisector of your BC. Now every point on this BC, suppose it is your S and T. So every point on the line ST will be equidistant from B also and from C also. Now the point where they are intersecting, where your PQ, perpendicular bisector PQ, and ST are intersecting, suppose this is the point of O. Now this O is the part of your PQ, it is lying on the perpendicular bisector PQ. That means this OA, distance OA will be equivalent to your OB, because every point on the perpendicular bisector PQ will be equidistant from your A and B. That means OA will be equivalent to OB. Now, if we will see the perpendicular bisector ST, then O is the point on the perpendicular bisector ST. That means the distance of this O point from B and C will also be equal. So, we can say OB will be equivalent to OC. From these two, what we can say is OA is equivalent to OB is equivalent to OC. That means if we will be taking O as the center, and either OA or OB or OC as the radius, then we can draw a circle which will pass through all the 3 points here A, B, C. That means O will be the center of the circle, and either OA or OB or OC as the radius of the circle, we can draw a circle which will pass through all the 3 points. So this is how we can get the center of the circle and the radius of the circle, and we can draw the circle if any 3 non-collinear points are given to us in any of the plane. So what we can conclude over here is theorem 10.5, that there is one and only one circle passing through 3 given non-collinear points. If 3 non-collinear points are given to us, then passing through these 3 non-collinear points, we can draw only one circle which will pass through all 3 of them. Already we have seen that if there is only one point or any 2 points given to us, then we can draw multiple circles passing through these points. But if 3 non-collinear points are given, then passing through all these 3, we can draw only one circle. Now suppose if there is a triangle ABC is given to us, then passing through these 3 non-collinear points, we can draw a circle which will pass through all these 3 vertices of a triangle. So such circle is known as your circumcircle. It is your circumcircle, and center of this circle is known as your circumcenter. This is known as circumcenter, and radius of this circle is known as your circumradius. So if there is a triangle, then passing through the vertices of a triangle, we can draw a circle. Just now we have said that if there are 3 non-collinear points, then passing through these 3 non-collinear points, we can draw one and only one circle. So if these 3 are the vertices of a triangle, then passing through these 3 non-collinear points that are vertices of a triangle, we can draw a circle which will pass through all 3 of them. Such circle is known as your circumcircle, and the center of the circle is known as circumcenter, and the radius is known as your circumradius. Now let's see one of the question of your exercise. Exercise 10.3. Question number 2 I am taking. Suppose you are given a circle, give a construction to find its center. A circle is given to us whose center is not given to us. So suppose this is the circle given to us. It is question number 2 of exercise 10.3, and we have to find the center of this circle. So what we will be doing is, on the circumference of the circle, we will be taking any 3 points anywhere. Suppose these 3 points we have taken on the circumference of the circle. So this is your point A, this is your point B, and this is your point C. Now what we will be doing is, we will be joining any 2 of them. AB we have joined and BC we have joined. We have joined these 2. AB we have joined and BC we have joined. Now similar to this, we will be doing the same thing. We will be making the perpendicular bisector of AB. Suppose from here B center, and more than half of AB will be taking the radius. We have made the arcs from A also and from B also, and this is the perpendicular bisector. Suppose this is the perpendicular bisector, your PQ. Now we will be making the perpendicular bisector of BC. Again B as the center, more than half of BC we will be taking the radius, making arcs from B also and making the arcs from your C also. Now again we will be joining these intersection points. The point where Your both the perpendicular bisector will be intersecting, will be the center of the circle, because this point where your both the perpendicular bisector are intersecting, this is the point on the perpendicular bisector PQ also. That means from this point O, suppose this is your O, then OA will be equivalent to your OB. And if this is the perpendicular bisector, suppose it is your ST is the perpendicular bisector of PC, in that case OC will be equivalent to your OB. That simply means your OA is equivalent to OB is equivalent to OC, or we can say O will be the center of the circle and OA, OB, OC will be the radius of the circle. That will be same, because in a circle radius is always same. Now let's understand the relation between the chord and its distance from the center. So what is the distance of any of the line from any of the given point? Suppose there is a line AB. Suppose I am taking this as the line AB, and any other point, say P, which is not on the line AB, which is somewhere outside the line AB, then the distance of this point P from the line AB will always be the perpendicular distance only. Whenever we are talking about the distance of any of the line from any of the point, then always and always it will be the perpendicular distance only, because perpendicular distance is always the shortest distance. Suppose this is your point O. So OP, if it is your 90 degree, if it is the perpendicular, then we will say that OP is the distance of point P from the line AB. Suppose I am going to take any other distance, say this is your PQ. Now PQ, if we are going to see, OPQ will be a right angle triangle in which PQ will be the hypotenuse, and we know that in a right angle triangle hypotenuse is the longest side. That means PQ will be greater than your OP. That's the reason OP will always be the shortest distance between the point and the given line, and it is always and always denoted as the distance between the point and the line. Distance between the point and the given line is always the perpendicular distance only. Now let's consider a circle. Suppose this is a circle. In this circle there is a chord AB. This AB is the chord and O is the center of the circle. Then what will be the distance of the chord AB from the center of the circle? That means if from the center of the circle we will draw a perpendicular on the chord AB, then this OP will be the distance of the chord AB from the center O. Distance of the chord from the center will be the perpendicular distance always. So we will say that OP is the distance of the chord from the center of the circle. We have already learned that if your chord will move towards the center of the circle, that means if I'll be taking any other chord, that is your CD, then the length of CD will be more than that of your AB, because CD is towards the center of the circle. Now if I am talking about the diameter of the circle, so suppose this EF is the diameter of the circle. So this diameter of the circle will be the longest chord as it is passing through the center of the circle. Now the distance of the chord AB from the center is your OP. Now distance of chord CD from the center is, suppose it is your OQ. Is OQ will be less than that of your OP. That means if length of the chord will be increasing, it will be moving towards the center of the circle, then its distance from the center of the circle will be decreasing. That means length of the AB, chord AB was less than that of your chord CD, but the perpendicular distance or the distance of the chord AB from the center will be greater than that of your distance of the chord CD from the center. Now if we will be talking about the diameter EF, so diameter EF is passing through the center of the circle. That means its distance from the center of the circle will be 0, because center of the circle is passing through your diameter. Now again, if we will be moving away from the center of the circle, then we will say, suppose it is your S and T. So the chord ST will be smaller than that of your EF, because EF is the greatest chord, your largest chord, that is the diameter of the circle. That means once we will be moving away from the center of the circle, the size of the chord or the length of the chord will keep on decreasing, it will keep on reducing. Hope it is clear what is distance of the chord from the center of the circle. If from the center of the circle we will be drawing the perpendicular, then it will be the distance of the chord from the center of the circle. Now let's see some of the theorems based on it. Theorem 10.6, equal chords of a circle or two congruent circles are equidistant from the center. That means if there are two chords of a circle, or if we have taken two congruent circles separately, in these two congruent circles, if we have taken two equal chords, in that case, the distance of the chords from the center of the circle will be equal. That we need to prove. So given to us is that AB is equivalent to CD. We have taken only one circle. In this circle, we have taken two equal chords. AB is equivalent to CD. These two chords are equal. It is given to us. And it is even given that OP is perpendicular to AB and OQ is perpendicular to CD. Because we are talking about the distance of the chords from the center. So distance of the chord from the center means the perpendicular distance only. That means OP is perpendicular to AB and OQ is perpendicular to CD. We need to prove that this distance OP is equivalent to OQ. This is equal. Distance of the chords from the center is equal if the chords are equal. This we need to prove. So what we will be doing is, we will be considering the triangle OAP. This triangle OAP, and we will be considering OCQ. These two triangles we will be considering. In the triangle OAP, the side OA is the radius of the circle, and in the triangle OCQ, OC is the radius of the circle. So OA will be equivalent to OC because they are radius of the circle. Now if we will be seeing OA is equivalent to OC, just now we have proved that these are radius of the circle. That's the reason they will be equal. Now AP, this will be equivalent to your CQ. Why? See, we know that the chords are equal. AB is equivalent to CD. It is already given to us that chords are equal. And we know that from the center, if we will be drawing the perpendicular on the chord, then it bisects the chord. Just now we have studied that perpendicular distance, if we will be drawing perpendicular from the center of the circle to the chord, then it bisects the chord. So if AB is equivalent to CD, so half of AB will even be equivalent to half of CD, and AP is half of AB and CQ is half of CD. That's the reason AP will be equivalent to your CQ. AP will be equivalent to your CQ because AB was given equivalent to your CD and P is the midpoint of AB. So AP will be equivalent to your CQ because Q is also the midpoint of your CD. So that's the reason AP will be equivalent to your CQ. Now from O, we have drawn the perpendicular on the side AB, meaning on the chord AB, and similarly from the center O, we have drawn perpendicular OQ on the chord CD. That means this angle and this angle, these two angles are 90 degree because it is perpendicular. So angle OPA will be equivalent to angle OQC, that is your 90 degree. So we will be considering these two triangles. We can say that by RHS, your hypotenuse are equal. Angle is 90 degree. One more side, that is your AP, is equivalent to your CQ. It is even equal. So one of the side angle and your hypotenuse are equal. So we will say that these two triangles are congruent by your RHS congruency rule. So triangle OAP is congruent to triangle OCQ. And we know that if triangles are congruent, we can say that by CPCT, their corresponding parts will even be equal. So what will be the corresponding parts for these two triangles? OP will be equivalent to your OQ. That means perpendicular distance of the chord from the center will be equal. OP is equivalent to OQ, and that was only to be proved. So this is how we can prove it, that if there are equal chords in a circle, then they are equidistant from the center also. Now let's understand the converse of it, that is theorem 10.7. That chords equidistant from the center of a circle are equal in length. Over here it is given that OP is equivalent to OQ. Two chords are given to us, that is AB and CD are the two chords. From the center we have drawn the perpendiculars on it. That's only the distance of the chord from the center. So OP is perpendicular to your OQ. and the length OP is equivalent to OQ, it is even given that the perpendicular distance or the distance are equal. Distance means your perpendicular distance always, just now we had discussed, whenever we are talking about a line and a point and talking about the distance between these two, that simply means it is a perpendicular distance always. So the perpendicular distance OP is equivalent to OQ. It is given to us. We need to prove that the chords AB and CD are equal. These two are equal in length. So given to us is that OP is equivalent to OQ. They are chords are equidistant from the center. So OP is equivalent to OQ. It is given to us. Along with that, it is given that OPA, this angle, and OQC, this angle is 90 degree because they are perpendiculars. OP is perpendicular to AB and OQ is perpendicular to CD. That's the reason they will be on 90 degrees. We have to prove that the chord AB is equivalent to chord CD. Now what we will be doing is, again we will be considering the triangle OAP and triangle OCQ. These two triangles we will be considering. In these two triangles, OA will be equivalent to OC because they are your radius of the same circle. So OA will be equivalent to your OC. OP is equivalent to your OQ. It is already given to us that the distance of the chords from the center is equal. That means OP is equivalent to OQ. It is given to us. Along with that, it is even given that OPA is equivalent to your OQC, that is 90 degree. So we will be seeing these two triangles. We can say that by RHS congruency, these two triangles are congruent. And if these two triangles OAP and OCQ are congruent, so we can say that by CPCT their corresponding parts will even be equal. That means AP will be equivalent to your CQ. AP will be equivalent to your CQ. Corresponding parts will even be equal. And if AP is equivalent to CQ, so twice of AP will even be equivalent to twice of CQ. We know that if from the center we are going to draw the perpendicular on the chord, then it bisects the chord. That means P will be the midpoint of AB. Similarly, from the center O, we have drawn the perpendicular OQ on the your chord CD, then it will be bisecting the chord CD also. That means Q is the midpoint of CD also. That means AP is equivalent to PB, right? And CQ is equivalent to QD. That's the reason if twice of AP is equivalent to twice of CQ, so we can say twice of AP means AP plus AP, and because both are equal, so we can say AB is equivalent to CD. That means chords are of equal length, and this was only to be proved. So this is how we can prove it. Now let's understand one of the question from your exercise 10.4. That is question number 5. 3 girls, Reshma, Salma and Mandeep, are playing a game by standing on a circle of radius 5 meter drawn in a park. Reshma throws a ball to Salma, Salma to Mandeep and Mandeep to Reshma. If the distance between Reshma and between Salma and Mandeep is 6 meter each, what is the distance between Reshma and Mandeep? So we are assuming that this is a circle in which this is the position for Reshma, this is the position for Salma, and this is the position for your Mandeep. Now the radius of the circle is your 5 meter. That means this is your 5 meter. O is the center of the circle we have taken. And the distance of your Reshma and Salma, this Reshma and Salma, it is your 6 meters. This is 6 meters given. And Salma to Mandeep is even your 6 meters. We have to find the distance between Reshma and Mandeep. This we need to find it out. So what we can see over here is that O is the center of the circle. OR, which is the radius of the circle, is your 5 meters. Distance between the Reshma and Salma is your 6 meters. Between Salma and Mandeep is 6 meters. We have to find the distance between R and M. The Reshma and Mandeep, we have to find this distance RM. RM length, we need to find it out. Now over here what we can see is, suppose from O, that is center of the circle, this RM is the chord of the circle. So from O we have drawn a perpendicular on the chord RM, which is intersecting the chord RM at your P point. That means P will be the midpoint of your RM. P will be the midpoint for the chord RM and this angle is 90 degree. Suppose I am assuming that this distance is your x meters. If this is x meters, this will even be your x meters because P will be the midpoint for your R and M. Now, if I'm going to consider these two triangles, triangle your RSP and triangle your MSP. If these two triangles I'll be considering, so what I could see is RS is equivalent to your SM. These two are equal. In the triangle RSP and triangle MSP, in these two triangle, RS is equivalent to your SM. It is given to us that this is 6 meters and this is also 6 meters. In these two triangles, SP is common for both the two triangles because it is coming in both the two triangles. So SP is equivalent to SP because it is common for both the two triangles. And just now we have said that OP is the perpendicular on the chord RM. That's the reason P will be the midpoint for your RM. And if P is the midpoint for RM, in that case RP will be equivalent to your PM. These two will be equal. And if three sides of this triangle are equivalent to the corresponding three sides of this triangle, so we can say that these two triangles are congruent to each other. These two triangles will be congruent to each other, and if these two triangles are congruent, so their corresponding parts will even be equal. That means your angle, this angle RPS will be equivalent to angle SPM. These two angles will be equal. They are the corresponding angles. So these two angles will be equal, but they are your linear pair of angles. These two angles are your linear pair of angles. So angle RPS plus angle SPM, they both will be, sum of these two will be 180 degree. So we can say angle RPS plus angle RPS, because they both were equal, so we have replaced SPM by your RPS. It will be 180 degree. So we can say angle RPS will be 180 by 2, that is your 90 degrees. That means this angle will be your 90 degree. And if this angle is 90 degree, we have already drawn OP as a perpendicular. So sum of these two is coming equivalent to 180 degree. That means OS is a straight line. What we can conclude from here, that OS will be a straight line. Now we will be considering the triangle ORS. Triangle ORS we will be considering. We know that the area of triangle is 1/2 into base into corresponding height. Whatsoever the side we are taking, accordingly corresponding altitude we will be considering. Now if we will be considering OS as the base, OS, which is again the radius of the circle only, so it will even be 5 meters because OS is a straight line and it will be the radius of the circle. So we will be considering OS as the base. In that case, RP, this will be the perpendicular, this will be the height. So area of this triangle ORS will be 1/2 into base I am taking as OS, that is 5, into perpendicular is your RP. So it could be written as 1/2, OS is 5 and RP we have assumed to be X. Now area of this same triangle could even be found by, if I'll be taking RS as the base and from O I'll be making a perpendicular over RS, then it is going to bisect the chord. From the center of the circle, I have drawn a perpendicular on the chord, then it will be bisecting the chord. That means if RS is 6, RQ will be 3. RQ will be 3. OQR triangle. OQR is a right angle triangle in which OR is the hypotenuse. So OR square, Pythagoras theorem I am applying, it is equivalent to OQ square plus RQ square. OR is 5. OQ we don't know. So let it be OQ only. And RQ just now we said it will be half of 6, that is 3. So it will be 3 square. So it will be 25 is equivalent to OQ square plus 9, or we can say 25 minus 9 is OQ square, or we can say 16 is OQ square, or we can say OQ will be root of 16. Positive 4 we will be considering. So OQ will be your 4 meters. That means if 6 is the base, then height will be your 4 meters. Now the area of the same triangle ORS will be area of triangle ORS will be 1 upon 2 into base is your RS into height is your OQ. So it will be 1 upon 2. RS is your 6 and OQ is your 4. So this is even the area of triangle ORS. This is even the area of triangle ORS. So both of them will be equal. So we will equate both the two areas. 1 upon 2 into 5 into x is equivalent to 1 upon 2 into 6 into 4. 1 upon 2 cancelled. So value of x will be 6 into 4 divided by 5. 6 4 is 24 divided by 5. This will be the real value of x. It can be find out 5 4s are 20. 20.4 will be the carryover. 5 8 is 40. 4.8 meter is the value of x, that is your RP. But RM will be twice of your RP. Twice of RP. Reason being P is the midpoint of your RM. This P is the midpoint of RM. So RM will be 2 times of your RP. So we can find the value of RM as 2 multiplied by 4.8. 9.6 meter will be the distance between your Reshma and your Manti. This is how we can solve this question. Now let's see what is angle subtended by an arc of a circle. We have already seen that if this is a circle, then if we'll be taking any 2 points on the circumference of a circle, then the part of the circle, this part of the circle is known as your arc. And if we will be joining these 2 points, then this will be the chord of the circle. If this O is the center of the circle, then if we'll be talking about this, so this is arc and this is your chord. As we are saying that if suppose I am saying this is PQ is one of the chord, another chord is say this is say AB. And if the length of PQ, chord PQ is equivalent to the chord AB, in that case your arc PQ will also be equivalent to your arc AB. This will even be the case. If there will be 2 congruent chords in a circle will be taking, then their corresponding arcs will even be equal. Similarly, we'll be saying, as we were saying, that if PQ is the chord, then angle subtended by the chord at the center will be, this is the angle, this angle. So angle subtended by the chord PQ at the center is your POQ. Similarly, we will be saying that angle subtended by the arc PQ at the center will be, because P and Q are the endpoints of the arc also. So angle subtended by the arc PQ at the center will be your POQ. It will be same. So angle subtended by, because we said that angle subtended by the 2 equal chords at the center are equal. So we will be saying that angle subtended by 2 equal arcs at the center will even be equal. So what we can conclude is, if 2 chords of a circle are equal, if we are saying that AB is equivalent to PQ, 2 chords are there, they are equal, then their corresponding arcs are congruent. That means this arc PQ will be congruent to your arc AB if chord AB is equivalent to PQ. Or we can say conversely, if 2 arcs are congruent, if we are saying arc AB is congruent to arc PQ, then we will say their corresponding chords will even be equal. In that case, chord AB will be equivalent to your chord PQ. And congruent arcs of a circle subtend equal angle at the center. Already we had said that if chords are equal, then they are subtending equal angles at the center. Now, if chords are equal, they are subtending equal angle at the center. So if arcs are equal, then they will be subtending equal angle at the center. Now we'll be seeing some more theorems based on this concept. Now let's understand one of the theorem based on the concept. Theorem 10.8, the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. That means if there is a circle with center O and PQ is one of the arc of this circle, then angle subtended by this arc PQ at the center will be angle POQ will be the angle subtended by the arc at the center, and angle subtended by this arc at any other point on the circle will be your PAQ. If we are considering a point A on any other point of the circle, in that case angle subtended by the arc PQ at A will be your angle PAQ. Over here we have to prove that angle subtended by this arc PQ at the center, that means this angle is double of your angle PAQ. Need to prove that angle POQ is 2 times of angle PAQ. Angle subtended by this arc at the center is POQ, and angle subtended by the arc at any other point on the circle is your PAQ. Then this angle is half of your this angle, or we can say this angle is double of your this angle. This we need to prove. Now over here 3 conditions could be there. One is your PQ is a minor arc, another could be your PQ is a semicircle, and third could be your PQ is a major arc. So we'll be seeing all the 3 conditions. So first condition we are considering over here we can see, first of all we are considering the triangle OAP. In triangle OAP we can see that OA is equivalent to OP. They are radius of the circle. OA is equivalent to OP because they are radius of the circle, and if they are the radius of the circle, then OAP will be an isosceles triangle. And we know that in an isosceles triangle, angle opposite to equal sides are also equal. So equal sides are your OA and OP are the equal sides. So angle opposite to OA will be your this angle. Angle opposite to OP will be your this angle. That means these 2 angles will be equal. So if this is angle 1, this will even be angle 1. Now in the triangle OAP, this angle is the exterior angle for this triangle. For the triangle OAP, if we have extended this OA, then this angle POB will be the exterior angle, and we know that the exterior angle is equivalent to sum of interior opposite angle. So if this is angle 3, so angle 3 will be equivalent to angle 1 plus angle 1, because interior opposite angle for this exterior angle will be this angle and this angle. So angle 3 will be equivalent to angle 1 plus angle 1, or we can say angle 3 equivalent to 2 times of angle 1. Now we will be considering another triangle, that is your OAQ. In triangle OAQ, again we can see that OA is equivalent to your OQ. OA will be equivalent to OQ because they are radius of the circle. And if they are the radius of the circle, then triangle OAQ will be an isosceles triangle, and the sides are OA and OQ are equal. So angle opposite to OA and OQ will even be equal. So suppose this angle is angle 2. So this angle will even be your angle 2. And this angle, suppose this is your angle 4, will be the exterior angle for this triangle OAQ. Angle 4 will be the exterior angle. So exterior angle 4 will be equivalent to sum of interior opposite angles. So we can say angle 4 is equivalent to 2 times of angle 2. Now if we will be adding equation number 1 and equation number 2, we will be getting angle 3 plus angle 4 is equivalent to 2 times of angle 1 plus 2 times of angle 2, and we can say angle 3 plus angle 4 is equivalent to 2. We could take common 2 times of angle 1 plus angle 2. Now angle 3 plus angle 4 could be written as your angle POQ. So angle POQ is 2 times of angle 1 plus angle 2 is your PAQ, 2 times of angle PAQ. And this was only to be proved that the angle subtended by the arc PQ at the center, that is POQ, is double of your angle PAQ. This is how we can prove it. Now, if it is a semicircle, that means PQ is a diameter. In that case, it is a straight line. So this angle will be on 180 degree also. In the same way, we can prove it. Suppose I am saying that we are taking the triangle APO. This triangle I am taking, in this OA will be equivalent to OP because both of them are radius of the circle. And if they are radius of the circle, the side angles opposite to these sides will even be equal. So if this is angle 1, this is even angle 1. And if this is your angle 3, so angle 3 will be angle 1 plus angle 1. That is angle 3 is equivalent to 2 times of angle 2 because angle 3 is the exterior angle for the triangle OAP. Similarly, we will be considering triangle OAQ. In this, OA is equivalent to OQ because both are radius of the same circle. And if these two sides are equal, then angle opposite to them will even be equal. So if this is angle 2, this will even be your angle 2. And for the triangle AOQ, this angle 4 will be the exterior angle. That means exterior angle is equivalent to sum of interior opposite angle. So we can say angle 4 will be 2 times of angle 2. Similarly, if we will be adding equation number 1 and equation number 2, it will be angle 3 plus angle 4 is equivalent to 2 times of angle 1 plus 2 times of angle 2, or 2 could be taken common. It could be written like this. So angle 3 plus angle 4 is your angle POQ and angle 1 plus angle 2 is your angle PAQ. And we know that PQ is a straight line. So sum of this angle, it will be a 180 degree because this is a linear pair of angle. So angle 3 plus angle 4 will be your 180 degree. So angle POQ will be your 180 degree is 2 times of angle PAQ, and we can say that angle PAQ will be 90 degree. That means angle in the semicircle. If an angle is formed in a semicircle, then it is a right angle. Angle in the semicircle is angle in the semicircle is right angle, because this angle will be 180 degree and this is half of this. So this angle PAQ will be your 90 degree. So we can say that angle in the semicircle is your right angle. Now similarly, we can take the third condition also when your arc PQ is a major arc. It is not a minor arc, it is a major arc. So again, the same conditions will be taking. We will be considering the triangle OAP. In this, OA and OP are the radius of the circle, and if they are the radius of the circle, triangle OAP will be an isosceles triangle. If it is an isosceles triangle, then angles opposite to equal sides will even be equal. We are assuming that these two are angle 1s and this is your angle 3. So this angle 3 is the exterior angle for the triangle OAP. So exterior angle will be your sum of interior opposite angle. In the same way, we can prove this also. Similarly, in the triangle OAQ, OA is equivalent to OQ because they are radius of the same circle. So the angle opposite to these equal sides will even be equal. So if this is angle 2, this will even be angle 2. And if this angle 4 is the exterior angle for this triangle OAQ, then exterior angle is sum of interior opposite angle. So angle 4 will be 2 times of angle 2. If we will be adding these two equations, we can say that angle 3 plus angle 4 is 2 times of angle 1 plus 2 times of angle 2. Angle 3 plus angle 4, 2 could be taken common. So angle 3 plus angle 4 is your angle POQ, that is reflex angle. Reflex angle POQ, it is equivalent to 2 times of angle 1 plus angle 2 is your angle PAQ. So this is how we can take all the three conditions, and in the same way we can prove that angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Now let's understand some more theorems related to circles. Theorem 10.9. Angle in the same segment of a circle are equal. That means if we have taken a circle, suppose this is a circle whose center is your O, and we have taken an arc PQ. So just now we have seen that by the arc PQ, angle subtended at the center will be your this POQ. And if we have taken a point over here on the remaining part of the circle, suppose this is your point A, then angle subtended by this arc at any other point on the circle will be your this PAQ. And this PAQ will be half of your POQ. Now on the same segment, that means if this PQ is the arc and on the same segment over here only we are taking any other point B also, then by this arc PQ, the angle formed will be your PBQ. Then this theorem says that angle A, this angle will be equivalent to your this angle. If this is X, this will even be your X. Angle in the same segment of a circle are equal. So just now we have seen that if PQ is the arc, then angle subtended by this arc at the center will be POQ, and it is double of the angle formed at any other point on the circle, that is it will be double of your PAQ. If this is X, this will be your 2X. Similarly, by this arc PQ, angle subtended at the center is your POQ, that is 2X. By the same arc PQ, angle subtended will be your PBQ also. So this PBQ will even be your half of your this angle POQ. That means it will even be your X. So these two angles will be of the equal measurement that was to be proved. Angle in the same segment of a circle are equal. That means if we are taking PQ as the arc, then in the same segment, if they will be making two angles, these two angles will be equal. Then your theorem 10.10, if a line segment joining 2 points, this is a line segment joining 2 points, subtends equal angle at 2 other points lying on the same side of the line containing the line segment. So we have to take any 2 points on the same side of this line segment. Either over here we will be taking 2 points, or we will be taking 2 points here. Suppose over here I am taking 2 points, and angle subtended by this line on these points are equal. That means if this angle is formed by this line segment and this angle is formed by this line segment, if this angle is equivalent to this angle, in that case the 4 points lie on a circle. That means in that case, if this is your A, this is your B, this is your C, and this is your D, then these 4 points will lie on the same circle. These 4 points will be concycling. Means from these 4 points, we can make a circle. We can draw a circle which will pass through all these 4 points. Like this, any of the circle could be made which will pass through all these 4 points. So this is even one of the theorem, that if there is a line segment joining 2 points, subtends equal angles at 2 other points lying on the same side of the line containing the line segment, then the 4 points lie on a circle. All these 4 points will lie on a circle. If the all 4 points will lie on a circle, then such points are known as your concyclic. These 4 points will be known as concyclic, because passing through these 4 points, we can draw a circle. That's the reason they are known as your concyclic. So if this condition is there, if there is 2 points are there, we have joined these 2 points and we have taken 2 points on the same side of this line segment, and angle subtended by this line segment at these 2 points are equal, then through these 4 points we can draw a unique circle can be drawn. That means these 4 points will be concyclic. Now what is concyclic quadrilateral? If there is a quadrilateral, suppose this is a quadrilateral, and through all the four vertices of this quadrilateral, if we can draw a circle, if any of the circle can be drawn passing through all the four vertices of the quadrilateral, then such type of quadrilateral are known as your cyclic quadrilateral. Cyclic quadrilateral. If there is a quadrilateral in which all the four vertices, through all the four vertices of the quadrilateral, we can draw a circle which will pass through all the four vertices of the quadrilateral, then such type of quadrilaterals are known as cyclic quadrilaterals. Now, what all are the properties of a cyclic quadrilaterals? Let's understand. Theorem 10.11. The sum of either pair of opposite angles of a cyclic quadrilateral is 180. If it is a cyclic quadrilateral, it is angle 1, it is angle 2, it is angle 3 and angle 4. Then in a cyclic quadrilateral, angle 1 plus angle 3 will be 180 degree. And angle 2 plus angle 4 will even be 180 degree. That means if it is a cyclic quadrilateral, then sum of either pair of opposite angles will be 180 degree. Sum of the opposite angles will be your 180 degree in the case of your cyclic quadrilateral. Now just converse of it is your theorem 10.12. If the sum of a pair of opposite angles of a quadrilateral is 180 degree, then the quadrilateral is cyclic. That means if there is any of the quadrilateral is given to you, this is a quadrilateral in which if angle 1 plus angle 3 is 180 degree and angle 2 plus angle 4 is 180 degree, if this is the case, then passing through these four vertices, we can draw a circle. A circle can be drawn which will pass through all these four vertices of the quadrilateral if the sum of opposite angles is your 180 degree. If there is a quadrilateral in which sum of opposite angles is 180 degree, then we can draw a circle which will pass through all these four vertices of the quadrilateral. This is your theorem 10.12, that if the sum of a pair of opposite angles of a quadrilateral is 180 degree, then the quadrilateral is your cyclic. That means from all these four, we can draw a circle which will pass through all four the vertices of the quadrilateral. Now let's see one of the question from your exercise 10.5. Using these theorems only, we'll be solving these type of questions. Question number 8 I am taking of exercise your 10.5. If the non-parallel sides of a trapezium are equal, this is a trapezium. Suppose the trapezium is your ABCD. If the non-parallel sides are equal, that means AD is equivalent to BC. Then prove that it is cyclic. Then we need to prove that this ABCD, this trapezium will be your cyclic quadrilateral. Now what we will be doing over here is, we know that in a trapezium, one pair of opposite side is parallel. That means AB is parallel to your CD. We know that. Over here it is given that AD is equivalent to BC. That means it is an isosceles trapezium. And now we have to prove that angle A plus angle C is 180 degree and angle B plus angle D is 180 degree. Because when this quadrilateral will be a cyclic quadrilateral, if the sum of opposite angles will be 180, then we can say that this trapezium is an cyclic quadrilateral. This will be cyclic. So what we need to prove is that if we will be proving that sum of opposite angles is 180 degree, then we can conclude that through these vertices A, B, C, D, we can draw a circle which will pass through all these four vertices. Now how we will be doing it? From A, we will be drawing a perpendicular on the side DC, and from B also we will be drawing a perpendicular on the side your CD. From A, we have drawn a perpendicular on the side DC. From B also we have drawn a perpendicular on the side DC. Now these two lines are the parallel lines. AB and CD are parallel lines, and the distance between the parallel lines is always same. That means suppose this is your say P and this is your Q. So AP will even be equivalent to your PQ because distance between the parallel lines is even equal. Distance means your perpendicular distance always. So AP will be equivalent to your PQ. Now we are considering triangle APD and triangle BQC. These two triangles we are considering. In these two triangles, it is already given to us that AD is equivalent to BC. It is already given to us. Now, because AP is the perpendicular distance between the parallel lines and BQ is even the perpendicular distance between the same lines. So, that's the reason AP will be equivalent to your BQ. And because perpendiculars we have drawn, so angle APD will be equivalent to angle BQC. Both will be on 90 degree. Right? So this side is equal to this side is equal to this side, and this angle is equal. So we can say that by RHS, because hypotenuse is equal, one of the side is equal and 90 degree is even there. So by RHS congruency, triangle APD is congruent to triangle BQC. Now, if these two triangles are congruent, so we know that if triangles are congruent, then their corresponding parts will even be equal. So we can say that angle D will be equivalent to your angle C. This angle D will be equivalent to your angle C. Now, just now we have proved that this angle and this angle is equal. Now we can see over here that AB is parallel to your CD and this AD is the transversal. AB, suppose I have extended it. AB is parallel to CD and this AD is the transversal. So this angle A plus angle D will be your 180. Sum of angle A plus angle D will be 180 degree because they are interior angles on the same side of the transversal. AB and CD are parallel lines. AD is transversal over here. So these angle A and angle D are interior angles on the same side of the transversal. So angle A plus angle D will be 180 degree. Similarly, your angle B plus angle C will even be a 180 degree because AB is parallel to CD and BC is the transversal. So this angle and this angle are the interior angles on the same side of the transversal. So angle B plus angle C will even be on 180 degree. Now suppose this is your equation number 1. This is equation number 2 and this is your equation number 3. So from equation number 1 and equation number your equation number 1 and equation number 2. From equation number 1 and 2. Instead of angle A, we have taken angle A only. But instead of angle D, we can take angle C also because angle D is equivalent to angle C. Just now we have proved by proving these two triangles to be congruent. So instead of angle D, we can write angle C also. So angle A plus angle C is your 180 degree. Angle A plus angle C is 180 degree. This was to be proved that opposite angles, if the sum of opposite angle is 180 degree, then we say that it will be a cyclic quadrilateral. It will be a cyclic trapezium. Similarly, we could have taken your equation number 1 and equation number 3 also. Equation 1 and 3. In that case, angle B we will keep it as it is. Instead of angle C, we can take angle D also because angle C is equivalent to angle D. So we can write angle D. It is equivalent to your 180 degree. So angle B plus angle D is 180 degree. So this is how we can prove that sum of opposite angles of this isosceles trapezium is your 180 degree, and because sum of opposite angles is 180 degree, so we will say that it will be a cyclic quadrilateral. If the sum of a pair of opposite angles of a quadrilateral is 180 degree, then the quadrilateral is cyclic quadrilateral. So this is how we can prove it. This is all from this chapter. Hope it is clear to you what is circle, what all are the parts of the circle, what all are the theorems of the circle. Soon we'll be coming with the more videos of other chapters of your class 9th maths curriculum. Thank you.